Hello everyone, I'm Sang Tian from Shanghai Jiao Tong University. Today we are going to introduce our work on real-time fluid simulation with atmospheric pressure using weak air particles. Our paper presents a particle-based approach to simulate versatile liquid effects under atmospheric pressure in real time. Atmospheric pressure can create interesting phenomena when interacting with liquids, such as Torricelli's barometer and U-tube manometer. Take Torricelli's experiment as an example. A mercury-filled glass tube is held upside down in a basin of mercury. The liquid inside the tube will fall down and eventually come to rest at a height of about 760 millimeters. The mercury column's height is independent of the shape and the tilt angle of the tube. However, it is common in computer graphics to ignore atmospheric pressure and assume a free surface boundary condition at the interface when simulating fluids. Air is a fluid with a very small density, and its coupling with liquid can be simulated as a two-phase flow. Simulating strong coupling two-phase flow with large density difference either incurs high computational costs or suffers from severe instabilities. Other methods considering air focus on handling the detailed boundary conditions of things like bubbles and thin features of free surface flows, but are not suitable for dealing with the contribution of atmospheric pressure on bulk fluids. To capture the liquid behaviors under atmospheric pressure, we present a particle-based method which uses weak air particles as a sparse sampling of air to track surfaces under atmospheric pressure stably and efficiently. Our weak air liquid coupling ensures the stability of two-phase flow with a large density ratio. We also present a surface force model consists of atmospheric pressure force and surface tension force. Our atmospheric pressure force correlates air density and pressure, and makes sure that the pressure increases as the air is compressed. Finally, we offer an interactive application where users can perform Torricelli's experiment and observe the interplay between air and liquid in real time. Our method focuses on position-based fluids, mainly because the position-based approach is stable, controllable, and well-suited for interactive environments. Position-based fluids rely on the position-based dynamics framework. To enforce incompressibility of fluid, PBF solves a density constraint and uses a spatial discretization in smooth particle hydrodynamics for density estimation. To solve the position correction constraints, PBF introduces a scaling factor lambda to process the position update after each constraint. In Torricelli's experiment, the mercury column is supported by the atmospheric pressure difference between the liquid surface in the basin and the liquid surface in the tube. On the right, we can see the orange ones represent weak air particles, the blue ones represent liquid particles, and the dark blue ones are the air-liquid boundary particles. To reduce the performance overhead, we set the radii of air particles to twice the size of liquid particles. The liquid surface in the basin is under atmospheric pressure, while the surface inside the tube is not. The shaded area above the liquid column is a vacuum. So we introduce weak air particles to track the air-liquid interface, and there are no interface particles inside the tube. To deal with the coupling of large density ratio, we use the PBF position correction formula. We make a distinction between the air particle set, the liquid particle set, and the solid particle set. For weak air particles, we introduce two small positive constants K to ensure the stability of the small mass air particles when colliding with the large mass liquid and solid particles. We neglect the contribution of air particles when computing the position update of the liquid particles. Once the weak air particles are simulated, the air-liquid interface can be accurately tracked by neighbor searching, and then the surface forces can be applied on the located boundary. Our surface force model consists of atmospheric pressure force and surface tension force. For atmospheric pressure force, He and his team formulated it as the sum of attraction forces, where P0 is a constant representing the atmospheric pressure. According to the combined ideal gas law, the pressure of the gas will increase when compressed in an enclosed space at an unchanged temperature. So we introduce a factor A for each air particle to correlate the pressure and the density. And using the SPH spatial discretization, which we have introduced before, we can get this formula to represent the relative density of the air phase. In addition, we take solid boundary particles into consideration to cope with the liquid particle jittering issues near the boundary. The video compares our method with and without considering solid boundary particles. We can see that our method can alleviate the particle jittering problem. Next, we apply the surface tension force proposed by Akinci and his team to improve our surface model. The first term calculates the cohesion force, which makes the neighboring liquid particles attract each other. And the second term is an additional force counteracting surface curvature to minimize the surface area. This video compares our method with and without the surface tension, and demonstrates that applying this force can smoothen the liquid surface and improve visual quality. As for the implementation, the simulation loop of weak air particles is outlined in this table, including the neighbor searching and the air-liquid coupling. We recreate the scene of Torricelli's experiment, where users can interact with the equipment. The mercury-filled tube is held upside down in the basin, covered by a slide at the bottom. After removing the slide, the mercury column inside will fall and stabilize at a specific height, depending on the corresponding atmospheric pressure and the liquid density. This video illustrates that the height of the mercury columns is the same in all tubes. According to the formula for calculating pressure, the vertical height is only related to the liquid density and the atmospheric pressure. Our surface force model can maintain the spherical shape of a droplet perfectly. We also provide a simplified U-tube manometer. When the air at the left side is squeezed by the piston, its volume decreases, pressure increases, and the liquid levels are no longer equal due to the pressure difference. We demonstrate that it is possible to simulate underwater air bubbles by introducing weak air particles and using our density-related atmospheric pressure model. As the bubble rises, its volume becomes larger. For conclusion, we have presented a comprehensive solution for real-time fluid simulation with atmospheric pressure. We introduce weak air particles to weakly couple with the liquid and track the liquid surface under atmospheric pressure, and presented a novel surface model composed of density-related atmospheric pressure force and surface tension force. One of the main limitations, which is also an interesting direction for our future work, is that the coupling force between air and liquid is not symmetric. The current weak coupling cannot enforce the incompressibility of air. In addition, the performance overhead can be further reduced by introducing adaptive mechanisms. That's all. Thank you for your attention.